when we did like the monkey hunter demo, nothing like combining those two words together. The monkey hunter, and if you remember, I had that bolt up there in the ceiling, and it was wrapped around with wire, okay? So basically, what I did is that I created a solenoid, okay? So that's why that thing is only a current, or excuse me, is only a magnet when there's a current going around it. So I is the amount of current that I send through the wire. So clearly, if there's more current, what's going to happen to the magnetic field? It gets stronger. Okay, cool. So N is the number of turns. So if you look at that bolt, I have wrapped that bolt probably with 200 turns. Okay, so I just sat there and wrapped that wire around and around and around and around. Because the more times I wrapped that bolt in that copper wire, the stronger that magnetic field became. So then, when I took that binder clip and attached that to a horribly drawn monkey, okay?
Same. That's how I feel right now.
It's a monkey, go with it. So, some of you asked, like, hey, what's a magnetic field? So let me explain it in terms of that bolt. So, iron has a bunch of random magnetic domains that exist basically you can think of each atom of iron being a very, very small magnet. So, before I turn on the wire, all of those magnetic domains were random, okay? So this is why the bolt itself is not a magnet, okay? But as soon as I turn on the current, then I take all of those random magnetic domains and I say, okay, you all need to line up. So once those random magnetic domains get within the magnetic field of that solenoid, then they all line up. Now, what I've done is that I've strengthened and created a magnetic field by using the bolt. So then that was strong enough to hold the monkey. As soon as I shut off the wire, what did those magnetic domains do in the bolt? They went back to being random, okay? So it's like, oh, great, crazy days. So that's why it stopped being a magnet as soon as I shut off the current, because then they went back to that original structure. So this is why one way to make a magnet, you don't make a very strong magnet. So if you take, like that bolt, for example, and you lay it on a north-south axis with the magnetic field of the earth, and you get it red hot, and you hit that with a hammer, and you force those magnetic domains to vibrate, then what's going to happen is that those are going to begin to line up with the magnetic field of the earth. And then it's going to become not a strong magnet, but it will become magnetized. Now, and that only works if you line it up with the north-south axis of the earth, because that's the magnetic field of the earth forces those to line up. So, now, if I want that monkey to hold up there, I obviously have to have a certain amount of current. So that's why I use that variable power source. If I have a very low current, that monkey is going to fall. So there's a threshold that I have to get so that the upward force from the magnet about overcomes the gravitational pull trying to pull the monkey down. I throw the switch, I open up the circuit, it's no longer a closed circuit, that's no longer a magnet, the magnetic domain's going back to being random, the monkey falls, we shoot it, we hit the monkey. Got it? Good, grand? Okay. Somewhere in this place.
No good questions.
Yeah,
You ask him.
no, you know, if you ask the least questions, you'd actually like to do most.
What's my name?
He's quiet down.
Making magic.
Okay. Danny, you still going?
Yep.
Okay. So here's what you've got on this first problem, and all of these first 5 questions deal with this question. So imagine that you have this. So here's your wire. You're looking at it like this. And this is how I have this system defined, the X, the Y, and the Z axis. So you want it to rotate about the Y axis. So you want it to spin like this, okay? So this thing is going to be here. You want it to spin in that direction, okay? In a clockwise direction. So what's the magnitude of the torque? That's just straight multiple choice dropped in races. Now, when you get to start answering, it's this question like number 1. Will a single magnetic field create a torque on all 4 sides? So you want to look at this problem from this initial starting position. Don't get wrapped up into, oh, it's going to change because it's going to rotate, and oh, it's going to be in. No, we're just looking at it from, okay, what's this initial static position and that magnetic field going through it? Yes, it would change as it spins. It's not the point of the story. When you get to question number 5, question 5, there is so much wrapped up in question number 5. So it's 10 centimeters on a side. The radius of the wire is 4 millimeters. The density of copper is 8.9 times 10 to the 3rd kilograms per cubic meter. I give you the strength of the magnetic field. The current is 10 amps. The wire is treated as a thin hoop. We're going old school moment of inertia. What is the angular velocity of the wire after 2 seconds?
Why?
Because I can. Okay? Because I can. So you got to go a whole bunch of old school on this one. Okay? You got to go a whole bunch of old school. But I will tell you that if you do that right,
That's the reason why I'm mistaken. They can't teach me at the moment.
if all goes well, when you get done, the angular velocity is going to be between 5 and 10 radians per second. Okay? So when you get done, and there's a whole bunch of calculations you have to do. You got to find the mass, you got to find torque. Now, quick refresher. Torque equals 2 things. It equals FR and
I fish.
I fish.
I fish.
Okay? Old school. I'm telling you, old school. Okay?
Current and
When you get to question number 8, okay? So on question number 8, let me paint the picture. So you've got a wire up here, and it's carrying a current of 2.5 amps
No, it's not.
in that direction on the paper. You have a wire hoop underneath it that's also carrying a 2.5 amp current going around clockwise. What you want to find is the net force acting on the system. Let me give you a hint. One's kind of going to get lifted up, the other one's going to get pushed away. So if all goes well on number 8, your final force, the net force, and you have to find, it's like a net force problem, should be something times 10 to the negative 6th. Okay? 10 to the negative 6th. 7 and 9 are, 9 is just that solenoid equation. So on number 9, you're just using this B equals mu naught I N over L. It's a simple, 9 is the simplest problem. Okay, I'm gonna tell you straight up, 9 is the simplest. 8's the second most complex, and 5 is the most complex. So, there you go. On number 6, to give you a hint, when you find that second current, that should be probably a little bit less than your age right now. I don't know, how old are you, Gep, Sean?
Don't ask him.
I'm 16.
Huh?
I'm 16.
So a little bit less than Gep, Sean.
So 15.
Case closed.
Ish, okay? Should be around 15. All right, I'm dying, you're on your own.
What are we doing tomorrow?
We're gonna go over this assignment, and then we're gonna watch some videos.
Yay.
So there's no homework over the weekend. The test over all of this is gonna be a week from Monday.
That's a long way.
Okay, it was either that or I have AP Chemistry and AP Physics back-to-back tests on Friday. So,
Okay, so our test is gonna be Friday?
No, because if you have a chem test, right, then you have no.
So our
Oh, but if you have just keep it this way.
otherwise it would have worked out. So I put tomorrow as kind of a buffer, because if I stick to my normal schedule,
It would have been best back, yeah.
I don't know whether I want to do the comp.
it's just kind of random, it's like gas laws, bonding.